In this lesson, you will learn about natural log and differentiation. First up, let's review the natural log function y equals ln of x. Now, this is the same as saying log base e of x. And remember that e is a constant approximately equal to 2.7, just so you know where it lives on the number line. Let's take a look at the graph of natural log of x. We can see that its domain is 0 to infinity. So that means we can only input numbers for x that are positive. For the range, we look at the y values, which go from negative infinity to positive infinity. It has a vertical asymptote here at x equals 0. And some of its attributes are that it's continuous, it's one-to-one, you can see as we go from left to right, it's always increasing, and that it's also always concave down. Now, a quick algebra review for one-to-one functions. Remember, a one-to-one function passes both the vertical line test and the horizontal line test. So every x value maps onto one y value, and every y value maps to one x value. Now we have an integral definition of natural log. Natural log of x is defined to be the integral from 1 to x of 1 over t dt, where x has to be greater than 0. And that's because of the domain of natural log. The domain is only positive numbers. That's why we have to make x greater than 0 here in this definition. Recall that when f is non-negative, then the definite integral finds the area under the curve. When x is greater than 1, let's consider natural log of x equaling the integral from 1 to x of 1 over t dt, this integral definition of natural log of x. So this definite integral is going to give us the area under the curve of 1 over t. So here's the graph of f of t equals 1 over t, and if we do the definite integral from 1 to x, then that means this area right here we know is going to be equal to the natural log of x, and that's going to be a positive number. It's above the x-axis, and we are integrating in the forward direction. Now, if we consider when x is between 0 and 1, and we look at that same definite integral, here's the graph of 1 over t. This time, we are integrating from 1 backwards to x, which means this area right here, which of course equals ln of x, and that's going to be negative this time, because even though this area is above the x-axis, we are integrating in the backwards direction. We are starting at 1 and integrating to x. If we started at x and integrated to 1, then this would be a positive area. Now I want to help you see how these two areas correspond with the graph of natural log of x. This one here, starting at 1 and going to x, corresponds to this part of the graph of natural log of x. As x gets bigger and bigger and bigger, then the area continues to get bigger, but at a slower and slower rate. And that's why on the curve of natural log of x, it continues to increase as x gets bigger, but it increases slower and slower and slower. Now compare that to the area under the curve here on this part when x is smaller than 1. We're integrating backwards, so remember we're going to get a negative value for that integral. But as x gets closer and closer to 0, this area is going to get bigger and bigger and bigger, and it's going faster and faster and faster, getting bigger. So that corresponds to this part of the graph of log of x, where the y value is heading off to negative infinity. Consider that the natural log of e, which we know is equal to 1, but now let's look at it in terms of the integral definition, where natural log of e is the integral from 1 to e of 1 over t dt. So e is the x value such that the area under this curve is equal to 1. So if we look at that on the picture here, we know e is right around here, about 2.7. And that means that when we integrate from 1 to e, we are getting this area, and that area is exactly equal to 1. And we know that the natural log of e is equal to 1. And just be reminded that natural log of e is log base e of e. And anytime the base matches the argument, you know the result is 1. Let's do a quick algebra review of the properties of natural logarithms. For a greater than 0 and b greater than 0, we have the following. The natural log of e equals log base e of e is equal to 1. We just looked at that a minute ago. Here, the natural log of 1 is equal to 0. Now, in its exponential form, this would look like e to the 0 equals 1. Here, the natural log of a times b turns into the natural log of a plus the natural log of b. The natural log of a divided by b is equal to natural log of a minus natural log of b. And the natural log of a to the n power is equal to n times the log of a. Now remember, this will work as long as a is positive. Now, if the exponent, n, is even, and x could be negative, this x here in the argument, then when we simplify, we say that the natural log of x to the n is equal to n times the natural log of the absolute value of x. Because remember, we need the argument of the natural log to be a positive number. So if it's possible for x to be negative, when it's in this form and we take it to an even power, that would turn it to a positive. However, when we write it in this form, we don't have that exponent here anymore. So if it's possible x could be negative, we have to take its absolute value when it's in the argument of the log. In this example, we have to state the domain of each in interval notation and simplify using the properties of logarithms. In part A, we have f of x equals natural log of x cubed. Now remember, when you're cubing, then the sign stays the same. If you have a positive and you cube it, it's positive. If you have a negative and you cube it, it's negative. So then the domain of this is that x must be greater than 0. So if we write that in interval notation, the domain is going to be 0 to infinity. So when we simplify this right-hand side, we know that the argument of our function is positive, so we can use this simpler form here and say that f of x is equal to 3 times the natural log of x. In part B, we have g of x equals log of x squared. Now we just need x squared to be greater than 0, and all we need for that to happen is that x just can't be 0. It's okay for x to be negative because when it gets squared, it turns positive. So our domain for this problem is negative infinity to 0 union 0 to infinity. Now this time we are in this special situation here where n is even. Our exponent is 2, which is an even number, and the argument x could be negative because our domain here includes negative numbers. So then this time when we simplify, we have to use this rule, which says that g of x will equal 2 times the natural log of the absolute value of x. Because in our domain we could potentially have negative numbers, we have to make sure they stay positive by putting the argument inside absolute values. In part C, we have h of x is equal to the natural log of this rational expression that has the quantity x squared plus 3 to the 5th in the numerator, and in the denominator is x to the 6th times the cube root of the quantity x plus 1. Now for the domain, remember that we need this entire argument to be positive. Now x squared plus 3 is always positive for all x, so we won't have any domain restrictions from there. We have an x to the 6th in the denominator, and x to the 6th is always greater than or equal to 0, and we can never have 0 in any denominator, so we know that x cannot equal 0. And then here we have the cube root of the quantity x plus 1. Now remember, cube roots can have negatives in the argument because you can find the cube root of a negative. It's also negative. But the argument of the entire log can never be negative. So to make sure that this quantity inside the cube root doesn't go negative, we have to say that x must be greater than negative 1. It can't equal negative 1 because that would turn this into a 0 in the denominator. So that means our domain is going to be negative 1 to 0 union 0 to positive infinity. In other words, x has to be greater than negative 1, except it can't be 0. And that's what this interval notation says. Everything from negative 1 to infinity except 0. Now we are ready to simplify this natural log. And we see that we have natural log of a over b, which means we can write it as natural log of a minus natural log of b. So this becomes natural log of x squared plus 3 to the 5th, that's the numerator, minus natural log of the entire denominator, which is x to the 6th, times the quantity x plus 1 to the 1/3. I'm going to choose to write this as a fractional exponent instead of the cube root. Now for this first term, we see that we have an exponent of 5. We can bring that to the front. So we have 5 times the natural log of x squared plus 3. We have a positive argument with an odd exponent, so we don't need any absolute value symbols here. Minus, now because here we're taking the natural log of a product, we're going to break that up into the natural log of x to the 6th plus the natural log of x plus 1 to the 1/3. So then this becomes equal to 5 times the natural log of x squared plus 3. And we have to distribute this negative sign. So we get minus. Now here we have an even exponent and we have an argument that could be negative. There are parts of the domain that are negative. So this is the case where we have to write this as 6 times the natural log of the absolute value of x, because we have to make sure that if a point from this part of the domain gets plugged in there, we're still taking the natural log of a positive. Remember, we have to distribute this negative sign to the second term, so we get minus 1/3 natural log of the quantity x plus 1. Now we didn't have to put absolute values here because we don't have an even exponent, and we also have an argument that's always going to be greater than 0. So this now is the simplified form. Now we can discuss the derivative of natural log of x. When we take the derivative with respect to x of the natural log of x, that means we are taking the derivative with respect to x of the integral from 1 to x of 1 over t dt. And we know that that's going to equal 1 over x by the second fundamental theorem of calculus. So then if u is a function of x, then by the chain rule, we would have the derivative with respect to x of the log of u would be 1 over u times du dx, or in other words, 1 over u times u prime, and this is the chain rule part, from here to here, or from here to here, and 1 over u times u prime can be written in a simpler form as u prime over u. So now we can say that the derivative with respect to x of the log of u can be written with this rule, u prime over u. In this example, we have to find the derivative with respect to x of the natural log of x to the 3rd power. So if we apply this new rule that we just learned and do u prime over u, then that means we would get in the numerator the derivative of x to the 3rd, which is 3x squared, over the argument, which in this case is x to the 3rd, and when we simplify that, we get 3 over x. Now the other way that we could do this is to expand using the properties of logs first. So if we start with the derivative with respect to x of the natural log of x cubed, we could write that as d by dx of 3 times the natural log of x. Now here, once again, we know that we do not need any absolute value symbols around the x, because since the argument was x to the third, we know that our domain is x greater than 0. So this argument is a positive number. Now, if we apply the rule of u prime over u to this function, natural log of x, we are going to get that constant 3 times 1 over x, because the derivative of x, our u prime, is equal to 1, and u is just x, that's who goes in the denominator, and then this becomes 3 over x, the same thing that we got before. So that tells us if we choose to, we may expand using the properties of logs first and then find the derivative, or we can find the derivative directly from the initial function. Sometimes it's easier to find the derivative when we first expand using the properties of logs. In this example, we have to find the derivative of h of x equals x natural log of x. It's time to check your understanding, so pause the video to try this one on your own, then restart when you are ready to check your answer. Because we have x times natural log of x, we know that we are going to have to use the product rule to find this derivative. So h prime of x is going to equal, let's jot down f prime g plus f g prime, so we don't forget any parts. We know that f is going to be x and g is going to be natural log of x. So then f prime is 1, and we have to take that times g, which is the natural log of x, plus f, which is x, times g prime, and remember the derivative of natural log of x is 1 over x, that's u prime over u. Simplifying, we have the natural log of x plus 1, and this is a correct answer. However, sometimes students will make the mistake of thinking that this plus 1 is part of the argument of the natural log function. So my recommendation to you is that you rewrite this as 1 plus natural log of x. And rewriting it in this form just makes sure that you don't accidentally include the plus 1 as part of the argument of the logarithm. In this example, we have to find the derivative of f of x equals the natural log of the square root of the quantity 3x plus 1. Let's take a look at the domain. We know that we will need 3x plus 1 to be greater than 0. Normally, for the argument inside of a radical, we would say greater than or equal to 0. But because this is on the inside of a natural log, we have to exclude 0. That's why it's simply greater than 0. That means 3x is greater than negative 1, which means x is greater than negative 1/3. So then our domain is going to be negative 1/3 to positive infinity. Those are the numbers that we can plug in for x. Now let's first rewrite f using the properties of logs, and we would get that f is equal to the natural log of the quantity 3x plus 1 to the 1/2 power. And now, because this argument is always going to be positive because of our domain restriction here, we know we don't have to worry about any absolute values. We can bring this exponent of 1/2 out front and take that times the natural log of 3x plus 1. Now we can find the derivative. So f prime of x, we're going to use the rule u prime over u, of course. That constant of 1/2 will come right down, and then applying u prime over u to the argument of the natural log, we will get 3 over 3x plus 1. So we can write this as 3 over 2 times the quantity 3x plus 1. In this example, we have to find the derivative of f of x equals the natural log of this rational expression here, where the numerator is x times the quantity x squared plus 1 squared, and the denominator is the square root of the quantity 2x cubed minus 1. Let's take a look at our domain. We know that we need this entire rational expression to be greater than 0 to satisfy the domain requirements of the natural log. So as we look at each piece, the x in the numerator will have to be greater than 0. We have this x squared plus 1 squared. Now x squared plus 1 is always greater than or equal to 0 for all values of x, so we don't have any domain restrictions here. In the denominator, we have a radical. The argument of the radical, normally we would set it greater than or equal to 0, but since it's in the denominator here, we will set it to strictly greater than 0. So 2x cubed minus 1 has to be greater than 0. So these two, remember, are an and. So we need this to be true, x greater than 0, and we need this to be true, 2x cubed minus 1 greater than 0. If we solve for x here, we would have 2x cubed greater than 1, which means x cubed is greater than 1 over 2, which means x is greater than 1 over the cube root of 2. We are going to skip rationalizing for now, so it's okay to leave this cube root in the denominator. So then our domain is going to be the combination of x greater than 0 and x greater than 1 over the cube root of 2, which means our domain will be from 1 over the cube root of 2 to positive infinity. And those will be the x values that we are allowed to plug into this function. Now let's use the properties of logs to simplify f of x. And it will equal the natural log of x plus, let's do two steps at once. We know we have a product here, that's why we're getting a plus sign. And we know for this term it has an exponent of 2, so let's bring that down and call it 2 natural log of x squared plus 1. And just a reminder, the reason we don't have to put absolute values around this, even though we had an even exponent, is because we know this is always positive. Now we have a quotient, so we will subtract. In the denominator, we would want to write this as 2x cubed minus 1 to the 1/2 power. So I'm going to bring that 1/2 power out front times natural log of 2x cubed minus 1. And it's always okay to do this simplification in one step if you feel comfortable. If not, do it in a couple of steps, and that's fine too. Now we are ready to find f prime of x, and we will be using the u prime over u rule for each of these terms. For the first term, natural log of x, u prime over u becomes 1 over x. Then we bring down the plus and that constant of 2. Applying u prime over u to this log, we will get 2x over x squared plus 1. Bring down the minus sign and the constant of 1/2. And then applying u prime over u to this natural log, we would get 6x squared over 2x cubed minus 1. Let's simplify, and we have 1 over x plus 4x over x squared plus 1 minus 3x squared over 2x cubed minus 1. Now at this point, we have to get the LCD and write this as a single rational expression. So this is going to equal, we know that our LCD will be the product of all three denominators, so x times x squared plus 1 times 2x cubed minus 1. Now this first rational expression is missing these two denominators, so we will have to take 1 times x squared plus 1 times 2x cubed minus 1. Then we bring down that plus sign. This rational expression is missing the denominator of x and 2x cubed minus 1, so we take 4x times x times 2x cubed minus 1. Then we bring down the minus sign and the 3x squared, and this rational expression is missing these two denominators, so we multiply times x and x squared plus 1. We continue to simplify, and in this first term we will need to FOIL that out. We will get 2x to the 5th minus x squared plus 2x cubed minus 1. From this second term, we are going to get 4x squared times 2x cubed is 8x x to the fifth, and then 4x squared times a negative 1 means we need to subtract 4x squared. From this third term, we have a negative 3x cubed times x squared, so we will subtract 3x to the fifth, and then negative 3x cubed times 1 means we will subtract 3x cubed. Our denominator stays the same, x times quantity x squared plus 1 times quantity 2x cubed minus 1. And then finally, we combine like terms. We have 2x to the fifth plus 8x to the fifth is 10x to the fifth minus 3x to the fifth means we have 7x to the fifth. Then we have 2x cubed minus 3x cubed, so that means we subtract x cubed. A negative x squared minus 4x squared means subtracting 5x squared. And then we have just this single constant term, minus 1. And in the denominator, we have x times the quantity x squared plus 1 times the quantity 2x cubed minus 1. And this is our final result. Next, we work with derivatives of natural logs involving absolute value. It turns out that the derivative with respect to x of the natural log of the absolute value of u is equal to u prime over u. So it is exactly the same rule as the derivative with respect to x for the natural log of u. To understand why, consider the domain of f of u equals the natural log of the absolute value of u. For the domain, we need the argument, which is absolute value of u, to be greater than 0. Now, from your college algebra days, you know that that turns into u greater than 0, or the opposite of u is greater than 0. And of course, this inequality is the equivalent to u is less than 0. So we have that u is greater than 0 or u is less than 0. Then that means our domain is negative infinity to 0 union 0 to positive infinity. That means u can be everything except 0. Now recall the definition for absolute value. Absolute value of u is the opposite of u when u is negative, and it's u when u is greater than or equal to 0, meaning u is non-negative. So let's look at the two cases in our domain. First up, we'll look at the piece of the domain for when u could be positive. So when u is greater than 0, the absolute value of u simplifies to be u. Then the derivative with respect to x of the natural log of the absolute value of u can be written as the derivative with respect to x of the natural log of u. Because whenever u is positive, absolute value of u gets replaced with u. Now this, we already know how to find the derivative of. It is equal to u prime over u. Now, let's look at the case when u is less than 0, which is this part of the domain. Whenever u is less than 0, the absolute value of u is the opposite of u, and this comes right from this part of the definition. Then the derivative with respect to x of the natural log of the absolute value of u becomes the derivative with respect to x of the natural log of the opposite of u, because we replace absolute value of u with negative u whenever u is negative. Now, to find the derivative of log of some stuff, we know we take the derivative of the stuff, so that would be negative u prime over the stuff, which is negative u, and this simplifies to be u prime over u. So it turns out that whether u is positive or u is negative, we get the same result for the derivative. So that means that the derivative with respect to x of the natural log of the absolute value of u is just u prime over u. And that's really great for us because it matches the formula that we already knew for the derivative of natural log of u. In this example, we have to find the derivative with respect to x of the natural log of the absolute value of tangent of x. Now we know that the rule is that we do u prime over u. So then this is going to equal the derivative of tangent x is secant squared of x, and we put that over u, which is tangent x, now this is going to equal secant squared can be written as 1 over the cosine squared, and tangent of x can be written as sine of x over cosine of x. So this will turn into 1 over the cosine squared of x times the reciprocal of the denominator, which is cosine x over sine x. Now this cosine of x will cancel one of these, so this simplifies to be 1 over the cosine of x times 1 over the sine of x. And finally, 1 over cosine of x is secant of x, and 1 over sine of x is cosecant x. Next, we learn an important technique, which is how to find a derivative using logarithmic differentiation. So logarithmic differentiation is this 4-step process, and I think the best way to learn it is to dive right into an example. So here we are given g of x is equal to x cubed times x plus 1 to the 5th times x plus 2 squared, and we are told that x is greater than 0. We have to find g prime of x using logarithmic differentiation. Now, something to pay attention to here, since we are told that x is greater than 0, we know that this factor will be positive, this factor's positive, and this factor's positive. And that's a good piece of information to keep track of as we work through this problem. Now, step 1 in the process of logarithmic differentiation is to take the natural log of both sides. So here, on the left-hand side, we take the natural log of g of x, we put the equal sign, and then on the right-hand side, we have to take the natural log of that entire quantity, x cubed times x plus 1 quantity to the 5th times quantity x plus 2 squared. Step 2 says to expand using the properties of logs. Now on the left-hand side, there's nothing to expand, so we just bring it down as it is, natural log of g of x. On the right-hand side, we can apply the properties of logs, and because we have a product here, we're going to turn it into the sum of 3 times the natural log of x plus 5 times the natural log of x plus 1 plus 2 times the natural log of x plus 2. Now in this step is where it was important to note that because x is greater than 0, this argument here is positive. Therefore, there's no absolute value needed. So even though we had an even exponent, in this case, we know for sure that the argument can't go negative because x is greater than 0. And if x is greater than 0, x plus 2 is certainly greater than 0. Now, step 3 says to take the derivative of both sides. We know that when we are taking the derivative of the log of u, we're going to be using the rule u prime over u. So on this left-hand side, we get g prime of x over g of x, and that's going to equal, on the right-hand side, this first term, we bring down that constant of 3, and then the derivative of natural log of x is 1 over x. Plus, we bring down the constant of 5, and we take that times the derivative of natural log of x plus 1, which would be 1 over x plus 1. Then we bring down the plus and the constant of 2, and we take that times the derivative of natural log of x plus 2, which is 1 over x plus 2. Now, step 4 in the process of logarithmic differentiation says to simplify and solve the equation for f prime of x. In our case, we will be solving for g prime of x. But first, we're going to need to do some simplification. So we'll leave the left-hand side alone. We have g prime of x over g of x. On the right-hand side, we have 3 over x from that first term plus 5 over x plus 1 for the second term plus 2 over x plus 2 for the third term. Now we will need to get the LCD. So our left-hand side stays g prime of x over g of x equals, on the right-hand side, we know that our common denominator will be the product of all three denominators, x times x plus 1 times x plus 2. This first rational expression is missing these two denominators, so we take 3 times quantity x plus 1 times quantity x plus 2 plus this second rational expression is missing the denominator of x and x plus 2, so we take 5 times x plus 2 plus this third rational expression is missing the denominator of x and x plus 1, so we have 2 times x times quantity x plus 1. Continuing to simplify, our left-hand side is g prime of x over g of x, and that's going to equal, in this numerator here, we can FOIL this out. Let's just do it right here. We know that would be x squared, and then we have 2x plus x, so plus 3x, and then last times last is plus 2, and then we have to take all of those terms times 3. So we are going to get 3x squared plus 9x plus 6. Here, from this second term, we have to distribute the 5x. Taking that times x, we will add 5x squared, and then 5x times 2, we add 10x. And in this third term, we have to distribute the 2x, so 2x times x means we add 2x squared, and 2x times 1, we add 2x. Now our denominator is going to stay the same, x times the quantity x plus 1 times the quantity x plus 2. So now we have g prime of x over g of x on the left-hand side still. On the right-hand side, we can combine like terms. We have 3x squared plus 5x squared plus 2x squared is 10x squared. 9x plus 10x plus 2x is 21x. And then the only constant term we have is 6. So we add 6. Our denominator stays the same, x times x plus 1 times x plus 2. Now remember that part of this last step is that we have to solve for g prime of x here. So the way we can do that is to multiply by g of x on both sides. Now, when we multiply by g of x on the right-hand side, let's write it in its full form, which is x cubed times the quantity x plus 1 to the 5th times the quantity x plus 2 squared. And remember that this is just g of x. So we're multiplying both sides by the same thing. It's just over here we want to write it as g of x, and over here we want to write it out in its full form. Now this left-hand side simplifies to become g prime of x And on the right-hand side, you can see we have a lot of canceling that's going to happen. But first, let's write this polynomial here. We have 10x squared plus 21x plus 6. Now this x in the denominator will cancel one of these, and we are left with x squared. The x plus 1 in the denominator here will cancel one of these, and we have x plus 1 to the 4th power. And the x plus 2 will cancel one of these, and we have to multiply times the quantity x plus 2. It's now to the 1st power. And this is our result. In this example, we are given y equals this rational expression with the quantity x minus 2 squared in the numerator and the square root of the quantity x squared plus 1 in the denominator. We are told that x is greater than 2, and we have to find y prime using logarithmic differentiation. It's time to check your understanding, so pause the video to try this one on your own, then restart when you are ready to check your answer. The first step is to take the natural log of both sides. So the left-hand side becomes the natural log of y, and the right-hand side becomes the natural log of the quantity x minus 2 squared over quantity x squared plus 1 to the 1/2 power. And again, I'm writing this using a fractional exponent in anticipation of what's coming up. Step 2 says to expand using the properties of logarithms. Nothing to expand on the left-hand side, so we just write natural log of y. On the right-hand side, we use the properties of logs, and we can expand that into 2 times the natural log of the quantity x minus 2. And even though this was an even exponent, we didn't have to put absolute value symbols here, because since x is greater than 2, we know that x minus 2 will be greater than 0. So since this is always positive, we don't need to put the absolute values there. So let's make a little note of that off on the side. We know that since x is greater than 2, that means that x minus 2 is greater than 0. Therefore, no absolute value symbols. Now here, to get at this one, we have to subtract 1/2 natural log of x squared plus 1. Next step is to take the derivative of both sides. The derivative of natural log of y is going to be y prime over y. And on the right-hand side, we have to bring down that constant of 2 and take it times the derivative of natural log of x minus 2, which is 1 over x minus 2, minus, let's bring down this constant of 1/2, and we take that times the derivative of natural log of the quantity x squared plus 1, which is 2x over x squared plus 1. Let's begin to simplify. we have y prime over y on the left-hand side. This first term is 2 over x minus 2 minus, in this second term, the 2 here cancels with the 2 here, so we have x over x squared plus 1. And we know that we're going to have to get the LCD. So we have y prime over y is equal to, our common denominator will be the product of these two denominators. So x minus 2 times quantity x squared plus 1. This first rational expression is just missing the denominator of x squared plus 1. So we have 2 times quantity x squared plus 1. Then we have the minus sign. This second rational expression is just missing the denominator of x minus 2. So we've got minus x times quantity x minus 2. So now we have y prime over y is equal to, let's distribute. For this first term, we will have 2x squared plus 2. And for this second term, we will get minus x squared plus 2x. Our denominator stays the same. Quantity x minus 2 times quantity x squared plus 1. Y prime over y is equal to, let's combine like terms. 2x squared minus x squared gives us x squared. Then we have plus 2x and plus 2. Our denominator is still quantity x minus 2 times quantity x squared plus 1. Now we are ready to multiply both sides by y so that we can isolate the y squared here. And remember, when we multiply by y on the right-hand side, we want to use this form where we have quantity x minus 2 squared over quantity x squared plus 1 to the 1/2 power. So remember, this is just y. On the left-hand side, the y's cancel, and we are left with y prime. On the right-hand side, we have this quantity x squared plus 2x plus 2. And this x minus 2 in the denominator cancels one of these, so we have left in the numerator quantity x minus 2. And in the denominator, the x squared plus 1 here is to the first power, and then we multiply that times x squared plus 1 to the 1/2 power, and it becomes the quantity x squared plus 1 to the 3/2 power. And this is our result.